So in the previous section, we went over things that we've done in the past, like, percent mass, molarity. These are things we've discussed in the past. So we're going to spend the rest of the time looking at a couple of other ways of measuring concentration that you might not be as familiar with, although in many ways you encounter them a little more frequently, or you will encounter them in the next couple of lectures. So let's go ahead and go back to our PowerPoint here. If I can find it. Guess what? I disabled it. I'm sorry. Let's go back here again. Okay. One more time. Here we go. If I can find it. Okay, here we go. All right. This is where we left off, right? We were talking about these practice exercises here. And what we're going to do now is we're going to continue and talk about other ways of measuring concentration. I just introduced you to the method of measuring molality. So let's do a calculation where we combine both in here. So what is the molality of a 5.86 molar ethanol solution whose density is 0.927 grams per milliliter? Okay, so ethanol essentially is alcohol, right? It's what we normally call alcohol in alcoholic beverages. Is actually ethanol, right? So let's review the formulas. For molality, you're going to find the moles of solute and divide by the kilograms of solvent. For molarity, uppercase M, it's moles of solute per liter. Now they're giving us the molarity. We have to find the molality. So a lot of this has to do with assembling a path. So what I need to have the moles of solute, right? So they didn't give us how much solvent we have in here either, or how much solution. So let's do this. Since we know what the moles per liter are, let's assume that we have 1 liter. They also didn't tell us what the solvent was, but I guess it's not important at this point. We would assume that it's water. It doesn't matter because we have the density of it. So let's start out by assuming that we have 1 liter of solution. So in 1 liter of solution, it says here we would have 5.86 moles of ethanol. They gave us the formula. They wrote it C2H5OH. The reason for putting that hydrogen kind of as a separate one is to remind us that these families of compounds called alcohols have that OH set of atoms that allows them to do hydrogen bonding. Hopefully you remember that from the previous section. So ethanol would have about 46 grams per mole. So that means that in 1 liter of solution, we have 270 grams of solute. Also, if we have a liter of solution and we know what the density is, we can find out, well, how much solution do we have, right? We have 1,000 milliliters, that's 1 liter. Density is 0.927 grams per milliliter. So that comes out to 927 grams of solution. So be very careful with these kind of problems. Again, when they give you the density, make sure you are aware of what they're telling you, the density of what. This is not the density of pure ethanol. This is the density of the solution that the ethanol is in, the total. And you're trying to find out the number of grams because what you want to find out in order to get the mass of solvent, right? Let me remind us of that. Since we're trying to find out what is the mass of solvent here, and I can't seem to be able to get this thing to work. Okay, my pen is not working. Sorry about that. We're trying to find the mass of solvent. We need to find out, well, how much of the solution is solvent, how much of it is solute. We know we had 270 grams of ethanol, and we have 927 grams of solution. To find out the mass of solvent, we're going to subtract the solution minus the solute. So 927 grams minus 270 grams, that's 657. But since the formula for molality requires kilograms, we need to roll the decimal period 3 spots to the left to make it 0.657 kilograms. Okay, everybody with me? Again, remember the strategy is I want to find out how many moles of solute I have, how many kilograms of solvent. The moles of solute I can get from the molarity if I assume I have 1 liter. But if I have 1 liter of solution, I need to find out, well, in that 1 liter of solution, how much of the mass of that is actually just the solvent. And we just found it here. It's 0.657 kilograms. So now we can calculate the molality, right? It's moles of solute divided by the kilograms of solvent. So we have, again, we assumed that we had 1 liter of solution. So we would have 5.86 moles of ethanol. And we just found out that we have 0.657 kilograms of solvent. So that is moles per kilogram of solvent. That's 8.92 molal, small m. Are there conditions under which the molarity and the molality might be the same value? It is not common at all. It's typically not the case. But I can probably come up with a scenario and numbers that would give us that kind of result. But what I'm saying is, don't look for a pattern as to where the molality is going to be same as, less than, or more than the molarity. Okay, there's no such trend. If you guys want to do some extra practice, you can ask yourself, what would be the percent by mass of this solution? What would be the mass percent? I'll let you guys work on that if you want. Okay, let me give you a few seconds to kind of wind down and download all that. And of course, the question you might ask is, if we have learned how to use molarities, and we have several ways of finding molarity or making solutions of a target molarity, and whenever we do chemical reactions, if we try to find out what is the amount of precipitate formed in a particular thing, or if we, in a precipitation reaction, or if we're doing a titration, what's the molarity of the unknown acid, or whatever the case, why do we need this other unit here of molality? Why complicate life a little more? So let's ask ourselves, what are the conditions under which we would use one versus the other? Okay, molarity is easier to measure. In other words, it's easy to measure the volume of a solution as opposed to try to weight the solution, getting its density, and then finding out, the kilograms of solvent. Now, if you're making it from scratch, you can simply weight out the solvent, weight out the solute, mix them up, and you don't really care what the final volume is. All you care about is what is the ratio of moles of solute to kilograms of solvent. But if you're trying to kind of describe or find the molality, it's easier to find the molarity because it's easy to measure volumes. The problem with molarity is that because the volume of a solution has to do with the amount of space that it occupies, and ultimately that means, well, how much space are the molecules taking up? If you change the temperature, you might find that those molecules either pull away more from each other or maybe collapse more towards each other. And so as you change the temperature, the volume changes. So a solution that is, let's say, 0.0115 molar at 25 degrees, at 95 degrees Celsius, the volume might have increased, and so the molarity might be less. So molarity varies with temperature. If I want to do an experiment where I'm going to be comparing a solution over a range of temperatures, in that case, then molality might be the better choice. Why? Because unlike volume, since molality is moles over mass, neither of those amounts change with temperature. And so if I'm doing an experiment comparing concentrations over a range of temperatures, molality might be a better choice because the mass doesn't change with the temperature. All right, so there you go. What kind of experiment is that? Glad you asked. So that'll be our final lecture of the semester. That'll be like our final actual lesson. We're going to talk about something called colligative properties, and most of them have to do with things that happen that have to do with temperature. For example, the boiling point, the vapor pressure, and things like that. Something called the osmotic pressure. We're going to talk about properties where molality might be the concentration unit of choice. All right. This is a table from your TRO book. I believe this might be from an older edition of it. It's a great table to have. If you guys want, you might want to copy this or have it handy because it has the formulas for all of the different forms of concentration, including some that we haven't discussed here. For example, you can see there in the middle bottom section, there's the percent by mass, parts per million, parts per billion, parts by volume, the mole percent, all these kind of things. I'm going to discuss one of those right now, and I'll let you guys look up the rest of them. Like I said, this table should be in your TRO book, but in the 5th edition, this is probably table more like 14.5 or something like that. So you'll have to look it up in your edition of the book. I'm sorry about that. And again, you don't have to memorize this. There's the study guide tells you which are the ones that you need to know. Now, what happens if you're trying to indicate the concentration of a solute in a large body of water? For example, I see a lake in there. If you wanted to, describe the concentration of the levels of mercury or lead, like a toxic substance in that lake, where the actual molarity or percent are very, very, very small numbers, is there a better way of indicating that? Or for example, in the case of water sourced in a city, many times they measure how much fluorine or fluoride actually is in the drinking water. Some communities still fluorinate their water. Some communities have gone away from that because of concerns about some people saying that it is not good for your health or whatever. Things like, for example, how do you express the number of particles or molecules of, let's say, carbon monoxide or nitrogen dioxide or other pollutants in air? If you were to try to express these in forms of percent or molarities, you're talking about 0.0000. It is going to be very, very small numbers where it becomes very easy for you to, miscopy a zero or put an extra zero where it doesn't belong or things like that. So what we do here is we're going to use a different type of unit for those types of very, very small concentrations. Let's think about percent, for example. What does percent mean? Well, percent really what it means is parts per 100. So for example, let's say that I have a solution that is 0.9% by mass, sort of what you get in an IV bag, which I hope you don't have to partake of. Hopefully you stay healthy. It'll say that it's 0.9% by mass, or the mass percent is 0.9%. What does that mean? Well, it means, yes, that if you divide the grams of solute by the grams of solution times 100, you get 0.9%. But percent means parts per 100. So that means that there are 0.9 grams of solute for every 100 grams of solution. That's what percent means. Now, if you had like a larger amount, you would say, well, let's roll the decimal period 3 points to the, 3 points over. And let's say we're going to say it's 0.9 kilograms for every 100 kilograms of solution. Again, parts per 100, that's what percent is. So what if instead of parts per 100, we said, well, parts per 1 million? In other words, parts of solute for every 1 million parts of solution. So let's say, for example, I have a solution that's 36 parts per million by volume. What that would mean is that there would be 36 milliliters of solute in 1 million milliliters of solution. So where percentage was parts per 100, parts per million, or ppm, is parts per 1 million. And that's the way you would do it. Let's say that we say that there are 36 parts per million of, let's say, mercury in a sample of water from some reservoir. Then that means there would be 36 grams of mercury for every 1 million grams of mercury. All right. Now, ppm, or parts per million, of course, you can kind of switch around the decimal period on both the top and bottom of that calculation. So if parts per million are grams of solute per 1 million grams of solution, you could also say, well, it's kind of like saying milligrams of solute per kilogram of solution. Most of the time, we are concerned with, of course, aqueous solutions. Based on the density of water, 1 gram per milliliter, 1 liter of water is 1 kilogram. When we talk about parts per million for an aqueous solution, the amount of solute is so small that for all practical purposes, we're talking about a mass of water here. So if I have a liter of water, that's a kilogram of water. If I have a liter of a solution that's so dilute that I'm having to calculate concentration as parts per million, you know what? That is 1 kilogram of water also. In other words, sometimes we don't bother trying to look for the density of such a dilute solution, right? So the difference in density for a dilute solution between the solution and pure water, same amount, is usually negligible. So again, parts per million, you see on the bottom there, is the amount of solute divided by the amount of solution times a million. We could use milligrams of solute per kilogram of solution. We could use milligrams of solute per liter of solution. Again, because in this case, we're going to assume that the solution is so dilute that the actual weight of the solution is the equivalent weight of the water. All right. Now, in some cases, the concentration is so extremely dilute that instead of parts per million, we might use parts per billion. Again, that'd be grams of solute per billion grams of solution. Let me take a little time out here. You guys realize that the word billion doesn't mean the same thing in the US than it means in a lot of the rest of the world. We were talking about parts per billion, and we were saying that in some parts of the world, the word billion doesn't mean what it means to us. For us, it means 1,000 million, in other words, 10 to the 9 items. But in many parts of the world, a billion is more like a million million, in other words, 10 to the 12. All right. So we're going to use the US definition here. We're going to divide grams of solute by the grams of solution. And of course, if it's water, this is so dilute that we essentially assume that talking about the milliliters of water is fine, of solution is fine. Times 10 to the 9th. That's our formula. So let's close out with a little practice exercise here, which I don't know if it made it into your PowerPoint notes. The EPA has set a limit of 2 parts per billion of mercury in water. If a 2-liter sample of water has 0.1 micrograms of mercury, is it safe? All right, let's do this. Let's go to our screen here. Well, that is not very sharp there. Let's see if I can focus it a little bit better. Okay, hopefully we can see it more or less okay. So remember the formula, grams of solute per gram of solution times 10 to the 9. Now, remember, in a very, very dilute solution, we assume essentially the grams of solution is essentially the grams of water because the density of the solution is going to be pretty much the same as the density of water. All right, so let's see if we can solve this. There's several ways you could do this, right? So let's start out by writing out our dimensional analysis. So we have 0.1 micrograms of mercury in 2 liters, 2.00 liters, but it's not going to matter because the 1 sig fig over there kind of takes it all. So that's what we have. So since we need grams on the top, I mean, like I said, you can do this many different ways. I'm going to just follow the dimensional analysis method just to keep it clear. So 1 microgram is 10 to the negative 6 meters, grams, I'm sorry, right? So that will cancel out the micrograms. And now in the bottom, I need grams of solution, but we said essentially that 1 liter of water is going to be what? 1,000 grams, right? Because we're assuming that the density of the solution is the same as the density of water. And that'll knock out. So now we have on the top, we have the grams of mercury. On the bottom, we have the grams of solution, i.e. water, times 10 to the 9. All right, you know what? I'm going to do it with you because I haven't done this problem either. So we're going to have 0.1 micrograms times 10 to the minus 6. That's the way my calculator handles scientific notation. Times 10 to the 9, divided by 2 liters, divided by 1,000. So that's 0.05. And it stays at 1 sig fig because that's what we brought in from this number they gave us here. So this is going to be 0.05 parts per billion. Okay, so do we need to report this to the EPA? Well, it told us that their limit is 2 parts per billion. And this sample has, 0.05. So I guess we are in the safe zone, at least for mercury in this, whatever the source of this water was. All right. All right. And I think, let me give you a few more seconds to write that down. And then we'll come back to wrap up our lecture. We're going to take off a little early today. So what I'm going to do is, let me leave that there for a few more seconds. See if anybody has any questions. You can either post them on the chat box here, or you can ask me. Okay, well, we're going to leave it here. Here's the plan. We will have a session on Wednesday. We're going to talk about solubility. What happens at the molecular level when a solution forms? What happens to the solute? What happens to the solvent? What kinds of interactions are happening in there? What are the thermochemical aspects of this thing? Yeah, it's going to be a pretty dense session there, all right?